Okay, this has been showing up all over the internet lately. If you take a chocolate ice cream and a vanilla ice cream cone and touch them together, something really weird happens. The vanilla gets transferred onto the chocolate and the chocolate gets transferred onto the vanilla in the exact same spot. This feels impossible. How do both of them transfer material in the same spot? This question has been getting tens of millions of views online, with people trying to explain it and still walking away confused. Now, at first glance, I just thought that the chocolate and vanilla were mixing at the surface. But the problem is that you can see that it's not like a chocolatey vanilla at the contact point. There's still a clear layer of chocolate and a clear layer of vanilla. No mixing that I could see. In this video, I'm going to show you what's really happening here, and along the way, we're going to uncover a surprisingly deep idea in physics: the difference between stirring and true mixing. This difference at first seems pedantic, but you'll see that it turns out to be a line between reversibility and irreversibility, between systems that remember their past and systems that forget it forever. And once you see it, it explains not just the ice cream, but everything from fluid flows to entropy itself. I've always been fascinated by this demonstration. If you take some corn syrup between two cylinders that can rotate, and then inject some dye blobs between them, you can turn the inner cylinder and it looks like this mixes all the colors together. Or so it seems. Actually, very little mixing is happening at all. What we're really doing is stirring. Stirring is the act of moving materials around. Nothing about the materials themselves has changed. The dye is still dye and the corn syrup is still corn syrup. We've just stretched the layers out. And this specific setup was deliberately designed to make it easy to reverse the exact stirring motion. Since I only turned a cylinder, I can undo that motion, and when I reverse it, all the layers go back to the same spot. This tells us something important about stirring. It is reversible in principle. As long as material is only being stretched and rearranged into layers, the persistent state still contains a record of the past. Stirred fluids can act like history books. For example, if I see these two cones, I can look at the gouge marks and layers and streaks and conclude which ice cream was moving in which direction. But in reality, the cases where we can clearly read history from stirred layers are rare, because most real stirring is not this smooth. The stirring I showed with the dye between the cylinders was laminar. But if I were to take a spoon and slowly stir dye in a cup, even if I tried to exactly mimic the spoon's motion in reverse, I couldn't undo it. Over time, especially when you've created lots of thin layers with lots of surface area, diffusion smooths everything out. Diffusion is the random thermal motion of atoms and molecules. Statistically, two initially separate groups of particles will spread out and interpenetrate. Once that happens, there's no way to reverse the process. True mixing has actually occurred. But if you were a physicist in the late 1800s named Joseph Lockschmidt, you would have had a serious problem with this explanation. The fundamental laws of motion are reversible. If you imagine a hypothetical all-knowing being that could track the position and velocity of every particle in a system, then at any moment that being could simply reverse all of those velocities. If that happened, every particle would retrace its exact path, and the system would unmix, and entropy would decrease. So Lockschmidt asked a deep question. If the laws of physics don't care which direction time runs, then why does entropy seem to only ever increase? This became known as Lockschmidt's paradox. Boltzmann tried to resolve this by arguing that entropy increase is statistical. Unmixed states are possible, but extraordinarily unlikely. This means entropy increases because mixed states are overwhelmingly more probable. But this was only a partial answer. The deeper resolution didn't come until quantum mechanics. Remember, in quantum mechanics, you can never define a particle's position and momentum past a certain accuracy. This is called the Heisenberg uncertainty principle. In diffusion, there are random bumps of molecules that depend on the momentum and position of every atom. And since those can't even be defined together, then that means that the true reversal or knowledge of the system is impossible. Entropy and information are fundamentally tied together, and there's an entire field built around this idea called information theory. Luckily, our original ice cream experiment turns out to be a reversible process. What's happening there is not mixing at the surface, it's something called gouging. Imagine two spheres sliding past each other. As they pass, each sphere overhangs the edge of the other just a little bit. that overhanging section gets stressed out and torn loose. So instead of atoms diffusing together, the chocolate scoop rips a chunk out of the vanilla, and at the same time the vanilla rips a chunk out of the chocolate. Those chunks get pressed onto the opposite surface at the same contact location. Both sides lose material and both sides gain material in the same spot. They're not mixing, they're taking bites out of each other. A surprisingly good way to model this is with colliding planets. On planetary scales, solids don't behave like rigid objects anymore. The forces involved are so enormous that rock behaves more like a thick gel. To show this, here's a physics-based simulation of two planets colliding on this program called Space Sim. I made one planet white and the other red, so it's easy to track the material. As they approach each other, you can see the first chunks get pulled out. Right at the moment they slide past, a flat contact layer forms. On one side it's red, and if you flip it over, on the other side it's white. Those layers slide, stretch, and tear just like the ice cream. And at the end of the collision, you're left with a red planet with white material stuck to it and a white planet with red material stuck to it, right at essentially the same collision point. So the next time you slide two ice creams past each other, remember that you're looking to a map of the past. That map doesn't last forever. Diffusion is always waiting to erase it, so read it while you can. And thanks for watching, and we'll see you next time.